Okay, so we're picking up with electrochemical measurements. And today, or on this video, I'm going to basically talk to you a little bit about some specific methods in electrochemistry. Now, unfortunately, I'm not going to be able to cover these in a lot of detail, okay? Reason being, it'll just take way too long. But if you want to follow up and learn more about electrochemistry, I would encourage you to take instrumental analysis with Dr. Pappas, and he'll tell you all about it. Now, where I'm going to start is more or less where we left off last time with this whole Nernst equation business, talking about changing the concentration of analytes and measuring a change in potential. We learned about the Nernst equation last time, which is really the quantitative basis for all of potentiometry. Now, to start off class today, what I'd like to do is consider this experiment over here. We've actually seen something like this before when we talked about argentometric methods and titrations. However, we're going to revisit it now, okay? Now, previously, we just decided it was a magical silver sensor. Okay? We dip a wire of silver down into a beaker, which contains aqueous silver +1 ion from the salt. And we measure the voltage with a voltmeter versus a reference electrode. And here, that's going to be one of those saturated calomel electrodes, okay? So remember, the reference electrode's job is to keep a very specific stable potential. So if the indicator electrode, which is the silver wire, experiences a change in potential within the solution caused by a changing concentration of silver, that can be sensed easily at the voltmeter, and we can quantify the silver concentration. Now, the redox reactions of interest are listed up here. The second one is for the calomel electrode. Of course, that involves the mercury, right? But the first one involves the silver. And this is the standard reduction potential for one electron reduction of silver, okay? So now that we kind of understand that these are standard reduction potentials, we understand the experiment, let's talk about deriving an equation for this particular sensor's signal, if you will, okay, or the voltage. So we start with this equation right here, which is familiar to us now. The cell voltage indicated at that voltmeter is equal to E reduced minus E oxidized. Simple enough. We talked about that equation last time. You just find the difference between the points, right? Voltage is a differential measurement. So what do? Well, we first start, I'm going to start over here first, okay? By taking the number for our saturated calomel electrode, 0.241 volts positive, and plugging it in for E ox. We're going to plug it directly in for E ox, and we're not going to do anything else with that because the saturated calomel electrode does not change composition, very stable reference voltage. But our sensor wire changes composition. So because of that, we need to write the Nernst equation for the other half cell, the silver half cell. And in my mathematics, that's written right here. Remember, it was E is equal to E0 minus 0.0592 over N times the log of Q. Now again, this is written as a reduction. So the product is this, silver solid, activity of 1. In the denominator, the silver ion is present, okay? So this is kind of what I'm starting with, this Nernst equation, and that's actually shown right there. The N is just equal to 1 because this is a 1 electron reduction, so hence they reduced it out to 0.0592, but otherwise, it's exactly what I've written up above. So all we're doing is we're taking the difference between these potentials to try to measure what the output signal is, or estimate what the output signal is, based on the silver concentration. And this equation now allows us to do that. Now we can simplify this equation down if we like to, okay? And that's what we're going to actually do here in this next step. Now we have this fraction, but I'm not super happy with that. So what I'm going to do is I'm going to use a property of logs. And it says if you take the logarithm of a fraction, that's equivalent to the log of the numerator minus the log of the denominator. Okay, so what I just wrote there in red is equal to that term that I just underlined, the log term, log of the fraction. Now, log of 1 is 0, right? And then we have minus log of AG. And we still need to multiply that here by this 0.0592. So 0.0592 times 0 is 0. And since it's a negative, if I multiply negative 0.0592 times negative log, I would get a positive 0.0592 log Ag plus. So I'm going to take that and I'm basically going to add it to the 0.799, my E0. And that's what I've done right here, okay? So I'm just basically doing mathematical manipulations. Still subtracting the value for the HTCl, the saturated kaolin electrode. That's the 0.241. So I'm working my way through this calculation and I'm simplifying the equation. Now what I can do is combine the 0.799 with the negative 0.241 to generate this number, the positive 0.558 once I do the combination. And I get that equation for the response of my electrochemical cell. E cell is what this voltmeter is going to read. And it should scale as 0.0592 times the base 10 log of the silver molarity or concentration. Again, really that should be activity, but we're going to use molarity plus 0.558. Now the cool thing about this equation is actually the equation of a line, and I tried to highlight that down below. So this number out by itself is the B term, like the y-intercept, right? This number is our m, or our slope of the line, and our x variable is the logarithm of the silver +1 concentration. So if I was try to sort of sketch out a graph, then what we might plot, my y is E cell, so that's my sensor reading, my voltmeter reading, and my x needs to be logarithm of Ag plus 1. Okay, so those are my variables, x and y respectively. My B is right about there, 0.558. And this relationship should be a line or linear, the slope of 0.0592. Okay. Now, electrodes which exhibit this sort of slope, which chemists oftentimes say is 59.2 millivolts per decade, are said to be Nernstian responsing. They're really completely perfectly responding to in accordance with the Nernst equation. And another thing that I really want you to point out here or notice, okay, is this is different in potentiometry, and it's really always the case. This x-axis down here is not the analyte concentration, it's the base 10 logarithm of the analyte concentration. So in the field of potentiometry, this is almost always encountered, is that the voltage that results doesn't respond linearly with analyte concentration, it responds linearly with the logarithm of the analyte concentration, okay? Very, very common relationship in potentiometry. Okay, so we see how we can build this sensor now, and it responds with the log of the concentration. We can make voltage measurements and relate that back to analyte concentration, and that's what's done in potentiometry. Now, the most favorite or famous type of potentiometric measurement is the pH electrode that's shown here, okay? What I'd like to do is take a few minutes just to describe what's going on here in the pH electrode, okay? So I'm gonna look at this picture over on the far right of the slide to help us. So first off, this is an example of what's called a combination electrode. Combination electrodes are cool because they contain both sensing element, the sensing electrode, and the reference electrode in one housing. Okay, both of those things in one housing. So it's like a probe that you just stick in your sample, and it's very convenient, right? Because you got everything you need, sort of a one-stop solution, right? So up at the top, we're going to have our positive and negative leads back to our voltmeter. It said it's a pH meter, but remember, a pH meter is nothing more than a glorified voltmeter. Now, what's inside this apparatus? That's what we want to pay attention to. So I'm going to start by looking at this positive lead, which is attached to this wire that goes down the very middle of the bore of our tubes. Okay, see, it's a concentric design already. So if I trace that wire all the way down to the bottom, what do I have? Well, I have a silver wire with a silver chloride paste down here. Okay, and notice that that is in a saturated solution of KCl. Isn't this a silver chloride reference electrode? Indeed it is. That's my reference electrode at the center of my electrode body. Okay, so we've seen that before. We're just building one of those basically inside this. Now for a second, let's also look at the other cell, okay? The negative cell. I'll trace that down, see what it is. Well, it's a silver wire with a silver paste in potassium chloride. It's another silver chloride electrode. Here and here, we built basically kind of the same thing both places, haven't we? So at first glance, you look at this and you say, gosh, the voltage would always be zero, right? I mean, I've got silver chloride on both sides. It's the same. I'm always going to get zero. This isn't going to work at all as a sensor. But we're going to do something a little bit different. What we're going to do is we're going to take a very thin glass membrane down here at the tip, and that's going to be our sort of our sensing element. Now, glass has some interesting properties, okay? One property of glass is that the surface of glass can exhibit a surface charge. Now, glass is silicon dioxide, okay? But what can happen at the surface in silicon dioxide, SiO2, okay? But what can happen at the surface is you form what are called these silanol groups, SiOH. And this H can actually be deprotonated, okay, at the surface. And the degree of protonation at the surface will depend upon the H plus concentration in the solution placed in contact with the glass. So if we have a lot of H pluses, what tends to happen is that surface will get protonated. The H plus will come and adsorb to this negatively charged glass surface. But if there's less H plus, that will happen to a lesser extent. Now, interestingly enough, this adsorption and differential adsorption to the surface of the glass will create over this membrane a potential or a delta V, a voltage drop, if you will, over this thin glass membrane. Now, if we're going to use this delta V, this voltage or potential difference across the membrane, we need to use it very systematically. And what I mean by that is that, well, again, voltage is a differential measurement. There'll be surface absorption on the outside of the glass. There will also be surface absorption on the inside. It seems like if we're going to make a sensor, we've got to fix one of these. And it can't be on the outside because that solution is going to change. We need to know the pH of that. So what we're going to do is inside the electrode, we're going to place a 0.1 molar HCl aqueous solution right inside this bowl. And that is always going to stay constant at 0.1 mole per liter inside that bowl, okay? And what that does for us is it sets a reference inside this fluid, right? 0.1 molar H plus. That's always the same. So it fixes the H plus absorption to the inside of the glass over there. Now outside, this is our test solution, isn't it? We want to know the pH of. So if we're at a very low pH, there's an abundance of H plus. Well, they bind to that glass quite readily, and that changes the surface potential. But if the solution's a high pH, then there's virtually no H plus around. So the surface is not going to absorb the H plus. It'll be barren of H plus, basically, or very little H plus present. So what this is going to do for us is it's going to create a voltage difference, what I might call a delta V, across that very thin membrane. And all we need to do is sense that voltage difference, okay? So the purpose of coming up with these two leads of essentially silver chloride reference electrodes is because one of those leads, the positive one, is on the inside solution, and the other lead is on outside of that, basically, okay? And the beauty of this is that this and this reference electrode just natively will always have 0 volts difference. But because we include this part of the apparatus in our circuit, that is this glass and the absorption of H plus, we actually can measure the difference in potential across that membrane. And that difference in potential can be related to the pH. Okay. Now the pH change, or the potential changes 0.059 volts for every factor of 10 change in H plus. Remember the logarithm of the concentration is how these potentiometric sensors respond? Indeed, we see that again. The electrode response is said to be Nernstian, okay? And up here at the top is then an equation for the equation by which these pH sensors basically respond. E is the cell potential, which is measured, and that's going to be equal to a constant, which is like our B term in a mathematical equation, plus 0.0592 times beta times delta pH, or change in pH. And that's essentially like that log of H plus term, okay? Now you say, okay, well, I thought that this was Nernstian, 0.0592 volts per decade, right? Indeed it is, but sometimes these electrodes do not respond perfectly Nernstian. Okay, so this factor beta is included in the equation. It's kind of, I hate to call it a fudge factor, okay? But it's kind of like another variable that can be adjusted to make the experimentally observed E, or cell potential, correspond better to the pH. And when you calibrate your pH meters, maybe you've used these before, you have to calibrate them with different buffers, usually pH 4, pH 7, pH 10. What that process does actually is establishes these two numbers within the memory of the electronic device. That's our voltmeter, or our pH meter. So you actually use a buffer to figure out what these numbers are. And that improves your quantitation just a little bit, okay? So that's usually why these pH probes have to be calibrated, okay? But nonetheless, pH electrodes, that's the most famous type potentiometric measurements. Now, I do also want to go on and tell you just about a few other methods, just ever so briefly, okay? There's electrogravimetric analysis, coulometric analysis, amperometry, and voltammetry. I just want to cover these briefly, just so you kind of know what this is about. Now, electrogravimetric analysis, I don't want to spend too much time on this, but what it is basically like electroplating materials. So let's just say that this beaker down here contains some copper ions. We can reduce the copper ions to copper solid. And what that's going to basically do is it's going to plate out the copper on an electrode inside this device, okay? Now we reduce on the cathode, so that must be where we're going to plate out the copper. Notice in this particular design, it's a gauze cathode. It's just like a little basket electrode that you put down in your beaker. Now the other electrode is the anode. That's made out of platinum, and that's spiral down here in the middle, okay? Because we need to have two electrodes. So all we're going to do basically is we're going to plate out the copper. And since it's electrogravimetric, that means we're going to make a mass measurement, okay? So what we're going to do for our mass measurement is we're going to measure the mass of that cathode previous to and after the plating experiment. Now the difference in mass will relate to the analyte quantity present. So we're just going to plate it out and figure out how many grams of material deposited on the electrode. It's just really as simple as that. And the thing is that if we're going to plate out the copper, we don't get that for free. We got to do a little bit of work to make that happen. In other words, the copper is just not going to spontaneously deposit oil. So we're going to have to make that happen. Now, how will that occur? We're going to drive this reaction by applying a voltage. This is why this technique is different than potentiometry. In potentiometry, you sit back and you measure the voltage. But in electrogravimetric analysis, you don't. You apply a voltage to drive a reaction to occur. So this is an active electrochemical technique. It's very, very different. It's active. How do we do that? Well, we are going to apply a voltage using a power supply, which is shown over on the far right. It's a variable power supply. What that electrical signal means is we're going to plug it into the wall and basically turn on and apply a voltage, a potential difference between our electrodes that will drive the reaction to occur. And we can measure the voltage applied using a voltmeter, and we can measure the current flow through the circuit using an ammeter. Ammeters measure current. Okay, so we're going to apply a voltage to drive the reaction to occur, and that's very different. Now, the spin-off of this technique, besides just measuring the mass, is coulometry. We talked about coulometry. It's where you measure charge, right? Well, this apparatus could do that for us. I just mentioned that we're going to apply a voltage to drive the reaction to occur. In the case that we were talking about earlier, it was copper 2 plus 2 electrons to plate out the copper solid on that platinum gauze electrode. So for every copper ion, 2 electrons are required to deposit the metal. Now we can apply this voltage and drive the reaction to occur, which is going to cause electrons to move through the circuit to get to our cathode where the reduction can occur. But we're smart about how these electrons move. Not only do we make them go through the wire, but we also make them go through the ammeter. Now they just pointed out the ammeter's job is to measure current. That's what it does. So I can measure the amps current in the circuit, and then I can use these terms that I learned about earlier, right? We learned an amp is a coulomb per second, and every mole of electrons has a charge of 96,500 coulombs. So we could use those variables or constants to basically figure out how many moles of electrons are present given a certain number of coulombs. And if I know how many moles of electrons are present, look, through the stoichiometry, I can certainly figure out how many moles of copper must have been reduced, okay? So it's a really pretty straightforward experiment. Now, the remainder of the techniques I'm going to tell you about generally employ this 3-electrode potentiostat, which is just an experimental apparatus for making these types of measurements. And indeed, even the one that I just told you about, the coulometry and the electrogravimetric, could use one of these devices experimentally. Now, as the name suggests, 3-electrode potentiostat basically contains 3 electrodes, or has 3 electrodes. No surprise, right? What about the word potentiostat? Well, what does that mean? Well, the potentiostat in electric chemistry is simply an experimental device or apparatus that is going to actively apply a voltage between electrodes. And not only does it actively apply the voltage, you can adjust the voltage that you apply. And also, these devices usually measure current as well. So it's kind of like a one-stop solution. It applies a voltage to our electrodes and it measures current, which is our analytical signal, of course, 3-electrode potentiostat. Now, I mentioned 3 electrodes. Well, what are these 3 electrodes? Well, they always have a working electrode, or it's sometimes called indicator electrode, okay? This is usually, we try to make this out of some sort of inert material. Platinum's pretty common, or maybe gold. Sometimes it's made out of carbon. The purpose being is that we don't want that electrode to react. We just want it to shuttle electrons into or out of our testing cell. So we make it out of inert material so we don't oxidize it, basically, okay? Now, our working electrode in this particular setup is shown in the middle. So I'll draw this arrow below the beaker. There's a beaker with a magnetic stirring bar in it. The one that's in the middle there is our working electrode. If you want to see what these typically look like, they're typically cylindrical or often cylindrical. And right down here at the tip, what people will do is the wire or the conductor will go right through the middle of an insulator. Here, that's paraffin, okay? But at the tip, there's a tiny little disc exposed. I call this a disc electrode, okay? Exposed tip, that's the millimeter or 2. And that's actually in direct contact with the solution. And that little disc is our conductor. So that would be like the gold or the platinum. And that's actually where the electrochemistry occurs at, the oxidation or the reduction reaction, right there at the tip. All right, now there's a few other electrodes, of course, 2 other really, in the 3-electrode potentiostat. So, where are these at? So let's take a look. Well, the next one is this one, the reference electrode. I already told you about reference electrodes. Remember, their job is to maintain rock steady voltages. Oftentimes we'll use a silver chloride. We can use a calomel electrode if we want to, but we basically put that down in our solution as well. In addition to that, we've got an auxiliary electrode. Now this is the new one, the third one that we haven't seen before. And this can just be a wire, basically. Oftentimes it's made out of platinum, again, due to its inert material or tendency. But what this does is it allows electricity to flow through the cell. It will not participate in the redox reaction. It just allows current to flow, so it doesn't have to flow through the reference electrode. So this is our 3-electrode potentiostat. Now look at the connections up top real fast. I want to highlight that. When I express a voltage or apply a voltage with my potentiostat, I do so such that the voltage is measured between my working electrode and my reference electrode. That is where the potentiostat applies the voltage. Working electrode, reference to reference electrode. That allows us to define the functional voltage of the working electrode because we got a stable reference point. And that's why it's so important to have this very stable reference point, okay? The auxiliary electrode's job is only to conduct current through the cell. Now, what can we do with this setup, this 3-electrode potentiostat? Well, one experiment we could do is amperometry. This is very similar to coulometry, but here current is measured rather than charge. Current is measured, okay? Now, earlier, remember I told you current is basically a measure of the redox reaction rate. If you measure current, that's what you're measuring. But if you think about it, if you set up one of these 3-electrode potentiostats, right, and you have analyte down here in the beaker, if you have a higher concentration of analyte, wouldn't that lead to a higher current if you're driving a redox reaction? And generally, that's true. So we can relate this current, which is a proxy of the redox reaction, directly to the concentration of our analyte. Now, how does this experiment work? Well, we turn on our potentiostat and we hold a voltage, or we apply a voltage first off, right? It's an active technique. We apply a voltage to drive a redox reaction to occur. And we hold that voltage at a fixed level, and then we just sit back and we measure current. Again, the current is a measure of the rate of the oxidative reduction process that occurs, and that depends upon the analyte's concentration, okay? Now, what's your data look like for such an experiment? And I should say that this experiment is not really a true amperometry experiment, but what would be an amperometry experiment is, let's just say you're measuring ascorbic acid in orange juice. And let's just say that you apply 0.8 volts, okay? So you apply positive 0.8 volts. And notice here it says volts versus the silver chloride. See how they labeled that axis? Very, very, very important to do that, okay? Label your axis, what your reference cell is. And that tells me something. Now I know what my reference point is. It's also very important. So in a true amperometry experiment, you might part the applied voltage at 0.8 volts, okay? And then you would measure the current. So the orange juice sample itself produced that current. And these other numbers here are actually spikes of the orange juice sample. So they had the orange juice sample and then they spiked it with more ascorbic acid. So you see the current keeps going up and up and up, right? And then you can make a plot of I sub L, which is called the limiting current, versus the concentration, and that would end up being linear. Now, the limiting current is basically where this current plot levels off, okay? Just to give you a heads up on this plot, you see what the whole plot is a plot of current versus applied potential. And you know, at very low applied potentials, the current's nil, isn't it? It's essentially zero. And the reason why is because at that applied potential, we're not driving or causing the redox reaction to occur. To make the redox reaction to occur, we really have to get up over this 0.5, 0.6 volts, don't we? Once we get to that level, the current takes off, right? We go up this slope, so to speak. And that's because at that applied voltage, that reaction is actually occurring now. We're driving it to occur, aren't we? Okay. So that's really what this plot's all about. Now, the limiting current is more or less where this plot levels off. And the reason why it levels off and it doesn't just increase infinitely is because at some point you've applied enough voltage to drive the reaction to occur. And any analyte molecule which comes in contact with the working electrode is basically going to be oxidized or reduced. Now, the thing is that for the reaction to occur, not only do we have to apply the voltage, but we also need analyte molecules to come in contact with the working electrode to transfer electrons, right? So at some point, what limits the current that can be produced in the signal is the rate of diffusion of the analyte to the electrode surface. And under those conditions, it's mass transport limited, you might say, okay? But interestingly enough, that's what limits the current, is that the analyte is going to diffuse to the electrode. Now, the higher the concentration, the higher the net flux of analyte diffusing to the electrode surface. So things speed up, we get higher currents, lower concentrations, lower currents. And that's kind of why this amperometry works out. Now, this is used a lot in analytical chemistry because chemists are really good at measuring currents. Remember, the basis of amperometry is applying a voltage, measuring a current. So let's look at an application, specific application. This is one, there are many. Turns out that sugars, different sugars, can be oxidized at an electrode, which is biased or held at a sufficient voltage. So we can force the oxidation of these sugars by applying a voltage. Now, what's required in this case at a specific electrode is a copper working electrode, which is specific for this silver, okay? Is that we apply a 0.55 volts versus silver chloride. So that's what we're going to apply to cause the oxidation. When silver molecules are oxidized, they produce a current. So how are we going to use this? Well, we're going to use this as a detector at the outlet of an HPLC column. Now, in HPLC, we separate molecules on a chromatography column, which is a stainless steel tube. It looks like that. When the molecules reach the end of the tube, they're separated, but we need to detect them, right? So we can use amperometry to do that. So the way that this works is a flow-through cell. Liquid flow is always coming from top to bottom, and it's going to perfuse through this cell at the bottom where the molecules will be oxidized. So down here in this block, we've got our working electrode, which is made from copper. That's that little black spot right there. Now that's in direct contact with the fluid, which flows through, all right? So if sugar molecules elute and are in contact with that copper working electrode, they can become oxidized and react, producing a signal. But of course, we still need two other electrodes, don't we, for our 3-electrode potentiostat. We need our reference and we need our auxiliary. And those electrodes both need to be in direct contact with the solution. So the people that published this paper, developed this, kind of came up with a unique solution up here on the left. What they did is they built a silver chloride standard reference electrode with that porous frit at the tip, okay? And they placed that reference electrode down inside of like a little conical chamber here, okay? Where it's in solution, or where it's in contact with the solution as the solution flows to the exit of the device, okay? And there's nothing wrong with that. As long as in electrical contact, it works. Interestingly enough, this outlet tubing was a piece of stainless steel. So you guessed it, they used that as their auxiliary electrode. They just clamp a banana clamp on there back to their 3-electrode potentiostat, and there's nothing wrong with making that your auxiliary electrode. So you've got your 3 electrodes, your working, your reference, and your auxiliary. You can plug those into your potentiostat, apply positive 0.55 volts, sit back and measure the current as analyte molecules elute through this cell to waste. Now, when they do this and they inject a sample containing sugars, they can produce a graph that looks like this, which is our chromatogram, based data in chromatography experiments. What it is, it's a plot of detector signal and time. Here's current, the redox current caused by the oxidation of these sugars. Once they reach that point, we plot it versus time. Now, every sugar which elutes will produce a peak. Really, any molecule which elutes that's able to be oxidized will produce a peak. So sure enough, they see multiple different peaks for multiple different sugars. Every single peak corresponds to some substance that eluted, was separated from the others, and individually detected at the outlet, okay? So amperometry can be used for this type of detector for HPLC. It's usually very sensitive, so it's popular, somewhat popular in analytical chemistry for molecules which can be oxidized or reduced. And it's quite sensitive because chemists are really quite good at measuring currents. Now, the next broad family of techniques that I want to tell you about are referred to as voltammetry. These all again, use that three-electrode potentiostat. We're also going to always apply a voltage to make a reaction occur. So none of that's going to be different. But where voltammetry differs from amperometry is that we are going to change the voltage here during the experimental run. During the experiment. That's what characterizes voltammetry. In amperometry, if it's really pure amperometry, you don't really change the voltage during the run. And in pure amperometry, you keep the voltage parked at a constant level. Like in this previous experiment I told you about, the voltage was always 0.55 during the entire experiment. It never changes, okay? It's always that. But in voltammetry, you typically do change the voltage. Now, there's a couple different types of voltammetry, really many even more than this. I'm just going to tell you about a few. We'll talk about linear scan voltammetry, pulse voltammetry, cyclic voltammetry, and then also something called anodic stripping voltammetry. It's kind of a fun experiment, as it turns out. They're all used for different analytes, different purposes, and I'll kind of expand upon this as we go. Now, if we're going to change the voltage during the run, we can think about, okay, well, what are the different ways to do that? I can change the voltage, make it more positive. I can change the voltage, make it more negative, obviously, right? I can change the rate at which the voltage changes. Okay, I call that the scan rate. I can change the actual shape of the waveform that I apply the voltage with. There's many, many different options. So electrochemists over the years have kind of explored this. Now, the simplest way to scan or change the voltage would be a linear scan. This is the linear voltage ramp or a linear scan experiment. Here, we change the voltage or applied potential over time in a linear fashion, okay? The scan rate, which is delta V, delta T, delta V, delta T, is the slope of this line. It tells us how fast we're changing the voltage per second, 1 volt per second, 10 millivolts per second, whatever it is, okay? But we just scan the voltage linearly. That's probably the first type of experiment that came to mind for you when I talked about scanning or changing the voltage. And there's nothing wrong with doing that. In fact, that was like the first type of voltammetry that people developed, and it works. But it turns out that there's a few limitations or drawbacks of doing that. Okay, and to understand these, let's consider this figure over here. I'm going to zoom in a little bit. Now, this is something that's very specific to this type of measurement, okay? But follow along with me here in your head, okay? Now, we're going to change the voltage of an electrode. Remember, we had probably one of those cylindrical electrodes with the disc at the bottom, right? And that was our active surface, and this has a lead, electrical lead that we put a wire back to our potentiostat, right? Now we want to change the applied potential to that surface. Does that come for free? And what I mean by that is when I apply a new voltage, I'm increasing it, making the voltage more positive, applied to the tip of that electrode, right? When I do that with my 3-electrode potentiostat, might a small amount of current flow in my system with the sole purpose of charging up that electrode or making it reach its new voltage, okay? And it turns out the answer is yes, okay? We get a small amount of current flowing through the circuit. And all that current's for is to basically charge up the electrode to the new applied voltage. And that's called the charging current. So next question, this charging current that results from changing the voltage on my electrode, does it have anything at all to do with my analyte concentration? No, it doesn't. That current flows just because we have to make that electrode a different potential. It has nothing to do with my analyte. But the problem is that my 3-electrode potentiostat will still measure that current. And the potentiostat has absolutely no way to tell the difference between this charging current and the actual current that we want to measure. Okay, so people came up with an interesting solution to this. So what they did is they decided that they could change the voltage or the electrical potential not linearly, but in steps. And this helps out a lot. Let's see why. Well, let's just say that you apply a step waveform in time to change the voltage applied to that working electrode with your 3-electrode potentiostat. So you step up, and then you wait a while, and then you step up again, you wait a while. Now you still get to the same point. You still get to the higher voltage. Oops. You still get to the higher voltage up here. You still get to the higher voltage up here, but you're just not scanning linearly. You're scanning in steps now. Okay. Now, why in the world might this be a good idea? Okay. Unfortunately, touched a button I wasn't supposed to, right? And it messed up my whiteboard. Okay, so why in the world is this a good idea? This stepping up the voltage. Okay, the reason why is that when you increase your potential right there on your electrode, that period in time is exactly when the current flows for charging the electrode to the new voltage. And if you stop increasing your voltage right there and let it level off, eventually that charging current is going to stop. So what happens is if you measure the current in time, and this is a brief period in time, okay, maybe milliseconds or less. What you see is so time equals 0 here is as soon as you step up the voltage to the new point, okay? What you see is that the charging current decays away to 0 once the new voltage is reached. So if you step up the voltage to the new point and you wait a little while, that charging current decays away, maybe at this point, okay? We'll say. It's gone because it no longer needs to be present. The electrode is at the new potential. No more current, no more charging currents flowing. But the second type of current, which we call Faraday current, and this is the one we want to measure, by the way. This is the one that results from the redox process. That Faraday current is not going to stop because analyte molecules still diffuse to the surface of the electrode, don't they? And they still undergo the redox process. They still produce a current. So the Faraday current doesn't stop, and that's the one we want to measure. So all we have to do is wait a certain time, delta T, right, after we step our voltage up. And after that, we're golden because we can measure the Faraday current independent from the charging current. So this step experiment is actually kind of a cool idea. And it's sort of a major advance because it gets rid of measuring this charging current. And the signal that we actually measure is only representative of the analyte concentration and not charging. Okay, so oftentimes people will do this step approach. Nonetheless, sometimes people will do linear scan experiments, kind of like the oldest type of voltammetry that there is. And this data plot actually up here actually shows examples of how this might work. This is time. This axis here is applied voltage. It's like up here at the top is the label for it. So it's potential versus the normal hydrogen electrode. So we'll reference back to the hydrogen electrode here. But nonetheless, applied voltage goes this way and time goes up and down on this plot. So the fact that this is a line basically goes to show that indeed we got a linear scan here. That's what's happening. Okay. Now up here is our signal over the course of this experiment. We've got potential on our x-axis. We've got current on our y. Now remember, we're measuring current. And if we do so, this is what it looks like. So initially, when the voltage applied is near zero, current's very low. But then once we get to about negative 0.4 volts for this particular experiment, and I'm not sure what the analyte here is, unfortunately, okay? But for this particular analyte, it starts to undergo a redox process for at about 0.4 volts negative. So when we get to that voltage as applied, current takes off, it jumps, right? And again, the reason why is because we are beginning to do the redox process at that point in time, aren't we? Beginning to do the redox process, the current jumps up way high as the analyte molecules are oxidized and reduced, and then kind of levels off up here, okay? Now again, the reason why it levels off is because the current becomes diffusion controlled up here. To produce current, we have to have analyte reacting at our electrode. And gosh, under these conditions, what limits the analyte getting to the surface is oftentimes diffusion. You can stir the solution and that helps, right? But these little details, whether the solution's stirred, whether it's not stirred, are actually all really important in electrochemistry, okay? So this is our linear scan experiment. If more than one substance is present that can undergo redox processes, you might see plots that look like this in a linear scan experiment. Notice that the current is very low at first, but then it jumps up, kind of levels off again before jumping up again. It's almost like a titration curve for a polyprotic acid, right? Well, the reason why you have these two regions of increase, whether it's this one or this one, okay, is because there are two analytes here. The first one begins getting oxidized or reduced at this applied potential, but that second one doesn't begin getting oxidized or reduced until a higher applied potential. So because the two substances are not oxidized or reduced at exactly the same applied voltage, you can actually measure them both in such an experiment, okay? Now, the other technique that I want to tell you about is anodic stripping voltammetry. This technique is used to measure metal ions. And historically, what we do for this is use a mercury electrode, a hanging drop mercury electrode. This is kind of a cool experiment because it's very specific to metal ions, but it's also kind of fun to talk about. So let me explain it real fast. So right here at the tip, I have an electrode. It's going to be your working electrode. Is a drop of mercury. Mercury is a liquid metal, right? So it's cool. It can conduct electricity, but it's a liquid, right? Which is kind of unusual. So you make a mercury drop electrode by putting a little bit of mercury in a pool, which should be up top, and then it kind of falls down through a very, very tiny tube, a capillary tube or a capillary tube, and it forms a drop right here at the tip. Now, you can apply a voltage to that mercury drop, and that's what we're going to do in this experiment. That's going to be one of our electrodes. So we hook it up to our potentiostat. We also have a reference electrode here. That's going to be a calomel reference electrode. So we're going to apply a voltage. It's going to be referenced to the calomel electrode. And we also have a wire that's going to serve as our auxiliary electrode. So all those, notice they go back to this potentiostat, right? Okay. So I get the idea how this works. There's a solution inside here. We're going to do some electrochemistry. Now, let's just say that there are ions in that solution, which in this technique is for measuring metal ions. Those metal ions are dispersed in the solution, different metal ions. There can be many, okay? I'm going to represent all the metal ions here as M+, just as a generic designation. Now, in their M+ forms, they're aqueous ions that float around in that solution. I want to measure them using this anodic stripping technique. So how do I do that? Well, it's a multiple step technique, as it turns out. The first one is I'm going to work to reduce the metal ions which are in the solution. And I'm going to carry out this reduction step for an extended period of time, maybe 10, 30 minutes or longer, okay? Now, why am I doing this? Okay, and what's the significance of this? Let me zoom back out so you can read along. So it turns out a really interesting thing happens at the mercury electrode. So we carry out the reduction of the metal at the mercury electrode, okay? Now, when the metal, +1, when the metal reduces to the solid element, mercury has this unusual property of being able to form amalgams with a large number of metals. Now, what does this mean? Okay, well, amalgam is kind of like a metal mixture. In this case, it's a liquid metal mixture. So I guess what we can think of this is that these metals, which are reduced, can basically dissolve into the mercury drop. They're reduced and they dissolve into the mercury drop. Now, interestingly, that causes them to accumulate in the mercury drop. So there can be a lot of metal ions here in this solution. And if I apply a potential which is sufficiently reducing to that mercury, I am going to reduce all of these metal ions and form this amalgam where the metal ions accumulate into the mercury drop. I'm basically collecting the metal ions into the mercury drop, if you want to think of that way, okay? So this first step in the process is a reduction step. It's a reduction step. Now you notice the name here, if you're perceptive, it's anodic stripping voltammetry. In other words, is where the oxidation occurs, right? So there must be an oxidation step. There's about to be. So after we accumulate the metal ions into the mercury, we then turn off the reducing potential and we scan the electrode voltage back towards oxidative potentials. We basically flip the sign on the applied voltage. We go back towards more oxidizing potentials. We scan back slowly. So what happens when we scan back to more oxidizing potentials? This is what happens. If we measure the current produced as we scan the potential, this is what we see. Might be kind of uninteresting for a while, but eventually we'll get a peak. Now this peak is for cadmium, okay? We'll scan a little bit more to more oxidizing potentials. Maybe we'll get another peak. This is a big one. This is for lead, right? Even more positive. Oh, we got a copper peak. So on and so forth. Multiple peaks for multiple elements. Now these materials were originally present in our sample. So why are we seeing peaks for them now? Well, what happened is in that first step, which is called a pre-concentration step, pre-concentration, we accumulated the cadmium, lead, and copper, which was dissolved in this solution, into the tiny mercury drop. We reduced those metals into the mercury drop where they form this amalgam or metal mixture, okay? We just collected them there. So we can keep this pre-concentration going for 10, 15, 30 minutes, an hour if you want to. And all the while, metal ions present in our sample will accumulate into that mercury drop. They just get collected there. It's actually really kind of a cool idea if you think about them. They get pre-concentrated, as we might say. Pre-concentrated, right? Now, what happens then on this scan? Well, remember I said I had to make my voltage more oxidizing. And that's what I do. I do it in a slow, controlled scan manner. I slowly increase the oxidizing nature of my potential. And I do that by applying higher and higher voltages with my potential step to my mercury electrode relative to the calomel reference. And eventually I get to the magic voltage where cadmium oxidizes. So any cadmium that was in that drop of mercury is going to experience an oxidation, and the reverse process will occur. The cadmium solid will now be oxidized to an aqueous ion plus N electrons. I'll put N plus as the charge, okay? It'll be oxidized, producing a current. That'll occur at a very specific potential That's a characteristic of cadmium. Likewise, lead can be oxidized at its own potential applied, as can copper. So by doing this experiment in a carefully controlled manner, I can sequentially oxidize these different metals at their very specific native natural oxidative potentials required to make this reaction occur. And since I concentrated all of them in that little mercury drop, I get these relatively large peaks because I pre-concentrated our analyte. Now, why is it a peak? Why does it go back down after you apply higher potential? Well, the reason why is because you just run out of that metal inside the drop. Remember, you accumulated a certain amount of metal, just a certain mass of your metal inside that drop, and eventually you just oxidize it all away, so the current stops. Okay, it's just gone. But you can certainly integrate the area under this curve, and that tells you something about how much analyte that you have present. So this is the anodic stripping voltammetry. Now, the last one I'm going to tell you about cyclic voltammetry, CV. And I'm going to post a video onto your Blackboard webpage that actually shows a cyclic voltammetry experiment that I performed in lab. You can actually see the trace on a oscilloscope. It's kind of cool because it brings this all to life. But cyclic voltammetry is another very interesting voltammetry technique. We are going to scan the potential. And what we're going to do is we're going to scan the potential back and forth. We're going to go one direction, make it more reducing or oxidizing, and then we're going to turn around and go right back to where we started, forming a circle. That's why they call it cyclic voltammetry. Now, in cyclic voltammetry, it is important to realize that your sample should not be stirred. And the reason why is because the magic of cyclic voltammetry occurs near the electrode surface. And to explain, consider one of those cylindrical electrodes. And this is kind of zoomed in. The electrode body, this is my working electrode, WE, so it's fed back to that potentiostat via wire, okay? So consider a molecule which exists in your sample beaker, which is electroactive and can exist in two forms, what I'll call the oxidized and reduced form. So let's just say our working electrode is originally applied a potential to it that's very, very reducing. So if we have the oxidized component in our sample, it might diffuse into the electrode surface, encounter that surface, and because it's so reducing, be converted to the reduced form. Okay, so nothing new right now, right? Well, if we do that for a little bit, okay, well, it seems like a lot of this oxidized material will become reduced. And we'll have a lot of the reduced molecules sort of floating around near the electrode surface, won't we? Now the oxidized material will still diffuse in slowly from the outside world, so to speak, okay? But we're going to build up the concentration of the reduced material close to the surface. Now, let's just say then after that, after the working electrode was very reducing, well, let's say we scan it back in the opposite direction and we make it all of a sudden oxidizing. Well, if this chemical compound that's in the proximity of our electrode, if it's electrochemically reversible, what I mean by that is if you can convert to substance interchangeably between oxidized and reduced forms, back and forth, right? It's like a cycle, back and forth, back and forth. Well, as I make this more oxidizing, then, interesting thing will happen. All of these molecules, which were reduced, will now do the opposite thing, and they're going to get converted back into the oxidized form. And this is all going to occur in this layer very, very close to our electrode surface. And that's actually why we can't stir the solution, because if we stir the solution, the oxidized and the reduced forms, boy, they're just going to get moved away from the electrode surface, and we may never see this reversible cycle, okay? So if we hit the scan rate just right, we'll say 0.01 to 1 volt per second. Interesting things happen. Interesting things can be observed in the data traces. Let's take a look. This is a data trace for a cyclic voltammetry experiment for this molecule right here. Now, oftentimes in electrochemistry, when we talk about these ions undergoing these reactions, cadmium 2 to cadmium 4, and iron 2 and 3, so on and so forth, like metal ions, right? But it turns out that lots of organic molecules can also undergo oxidations and reductions, and this is actually an example of that, okay? We know we're oxidizing and reducing this molecule shown over here, and the associated data is for that. And you don't have to know the molecule, just know that organics can sometimes also undergo these types of processes. Okay, so what we're going to do is in this experiment, we're going to start right here. It's our starting potential. So somewhere around 0 volts versus the reference electrode. You notice down here, it doesn't tell us what the reference electrode is, so we don't know, do we? We're kind of clueless. So I can explain the figure, but I don't know what this is referenced to, so I don't know the absolute voltage, but nonetheless, that's why you need to report that. But we're going to start right here. We're going to scan towards the negative, or the, oh, sorry, they reverse the axis, so it's positive. Okay, we're going to stand towards the positive, which is more oxidizing. And eventually, so we have the reduced form, eventually we get to the point when the oxidation takes off and the current peaks. Now the current goes down here, or it's down direction. And the reason why is that's just a convention for the oxidative current or the anodic current. We just show that pointing down, okay? But it means that reaction's going. So there's a current. It goes through a peak, and then it drops back off. And the reason why is because our solution's not stirred. So even though we're going to more oxidative potentials, the current drops. Our solution's not stirred, so we essentially consume reduced materials near our electrode surface, dropping the current off. But now we're at that point where we've got a lot of the oxidized material. So we stop and we go back the other direction with our scan. Now we go to more negative voltages. We have been going to more positive. We got the oxidation to occur. Now we're going to go back to negative. What happens is, once you get back to a certain voltage where the reduction can occur, the current starts taking off and we get the reduction of cathodic current. Go through a peak, drop back off again. The reason why we drop back off is because, well, now we're basically taking all that material which was oxidized and reducing it back into the other form. So we're going back and forth in this reaction between these two different forms, with the action occurring over here, basically, okay? We're cycling because we're spinning the voltage the two different directions. We started making it more oxidizing, and then we turned around and made it more reducing, okay? It's a really cool experiment because it results in a cycle. Okay, and now this is a reversible cycle as shown here, but they're not always reversible. Sometimes molecules might get oxidized, and then before they can be reduced, the molecule might fall apart and decompose, or it might react with something else if we make a very reactive molecule upon oxidation. So again, they're not always reversible, but this one's very reversible, okay? And the way you can tell that is by looking at the magnitude of the peak currents. It should be about the same if it's going to be reversible. Okay, so this is cyclical telemetry. Okay, so I'm going to show you a video of an actual experiment on Blackboard. I'll be sure to post that. Just take a look at that. It's kind of interesting. I think it's a couple minutes long, not very long, but you can actually see the trace being drawn out during one of these CV experiments. And with that said, I think this is about all the time we have to consider electrochemistry. So I'm going to stop this video and we're going to move on to the next topic.